Okay guys, let's go ahead and take a look at this problem. What we have is a region right here bounded by this curve, y is equal to e to the negative 2x, for the x values between 0 and the natural log of 2, and then of course with the x-axis. So for the y values between 0 and clearly up here at 1. Okay, so what we're going to do is we want to find what the volume is by using the disk method when we take this curve and we revolve it around the axis. So what is it going to look like? Well, if I extend this line like this, and this, if I reflect it, it looks something like this, close enough, and we're going to revolve, like this around. Okay, so we're going to have some kind of cone type looking figure that's flat on the top, okay, flat on the bottom. It's got this volume in the middle here. So how are we going to do that? Well, what we have to do is we have to figure out if we take an individual slice of that, we have to find what the area is for this. Okay, so let's go ahead and do that. So the area, okay, as a function of the radius is going to be equal to, now the radius, typically area is equal to pi r squared, but here the radius is given by this function. So what we have is the area, instead of using r, the area as a function of the function x is equal to this. So this is the area of a cross section of the figure formed by rotating around. Now what we need to do is multiply it by the width of the figure, and so what we have is a circular, a very, very thin, in fact, a ridiculously thin disc that's formed by moving just slightly to the right or the left, whichever way you want to think about it. And so what we've got is the volume of just one of these guys. The volume is going to be equal to the area multiplied by its width. So the area is this, and we'll multiply it by its width, which is, we'll call it delta x, just a little bit of x this way. Now what we want to do is we want to add up all of those guys together, and there's an infinite amount between 0 and the natural log of 2. Okay, so to do that, to add up all of them, the total, the overall volume as a function of x, okay, will be equal, well, actually I shouldn't even say it's a function of x. Let me just write it like this. The volume is equal to the integral of 0 to the natural log of 2, because that's what x is varying between. Okay, of pi, I'm going to pull the pi out, f of x squared, and now this delta x becomes dx here, because this is infinitely small. Okay, so what we're doing is we're adding up all of these disks that are forming up the volume. Okay, so we need to go ahead and do some substitution here. So we know, we've got some formulas. We know that the function, the radius values, are all e to the negative 2x. Okay, so we've got pi times the integral of 0, natural log of 2, which is just a number, okay, e to the negative 2x squared dx. So that will be e to the negative 4x dx, because when you take something and raise it to, and it has a power, and you raise it to another power, you're going to multiply these guys together. So we get this. So let's continue. So what we need is we need an antiderivative for this. Okay, and what I'm going to do is I'm just going to do a substitution. Okay, u sub. So I'm going to say let u be equal to negative 4x. Then that implies that du is equal to negative 4 dx. Right? If you're confused on where I'm getting this from, one way to think about it, okay, is if I had u is equal to negative 4x, then du dx, using the Leibniz notation, would be equal to this. And if we just multiply both sides by dx, okay, we would end up back here. Now, that's not, depending on how you approach this du dx for the definition, that's not completely correct. You can't actually multiply both sides by dx unless you're looking at these guys as infinitesimals. But for all practical purposes, we can do that. It's just not mathematically sound, okay? But everyone does it that way. So don't worry, it'll still get you the correct answer. So that's what we're gonna go ahead and do. If you're really curious about why we can't move this, feel free during my office hours to log on, and I'll do a better job of explaining to you why we can't move those guys around. Okay, but we can play around with them as if they were able to move around. So what we have based off of this is that du divided by negative 4 is equal to dx. Okay, so that gives us some information here to replace. So what we're going to do, I'll get to my bounds in a second here, but this is going to be e to, now I replaced negative 4x with u. So e to the u, and now dx, well, what is dx equal to? We have to replace that, because if I just leave dx in here, these variables don't match. Okay, so that's no good. So I want to have du in here. Well, I know that dx is du over negative 4. So we're going to take this dx right here. We're going to replace it with du over negative 4. Like that. And in fact, we're going to pull this negative 4 out in just a second, because it's just a constant. So there's no reason that we can't move it out. Now the bounds. Okay, there's two ways to look at the bounds. We could replace the bounds right away. Okay, and how we replace the bounds is we say, well, x, our original variable, vary between 0 and natural log of 2. So we look at the relationship between u and x, and we use that to replace the bounds. Let me go ahead and I'll do that over here as a side note. Now this is, in fact, this is not the way that I normally do it, just because I think this is a little bit harder. It's a little bit more cumbersome with some of the values here. Okay, so I usually end up just going back and replacing this u after I do my integration. But the correct way of doing it, the better way of doing it, is to say, okay, well, x was equal to 0 and x was equal to the natural log of 2. Those were the two bounds for x, right? If you look at x, the x-axis, it went from 0 to natural log of 2. So if x was 0 and this relationship existed, then what is u? So just real quick here, if u was equal to negative 4x, that implies that u over negative 4 is equal to x, right? So I can replace both of these with u over negative 4. Look at that. Okay, so this one becomes u is still equal to 0. This one over here becomes u is equal to negative 4 natural log of 2. Like that. Okay, so we would replace those guys in here. So u goes from 0 to negative 4 natural log of 2. This is one way of doing it, is by changing your bounds. We made a substitution, so our bounds are no longer good, and our dx was no longer good, so we had to do all that replacing. Okay, now we pull the negative 4 out. So this is pi over negative 4 integral from 0 to negative 4 natural log 2 e to the u du. Now I'm looking for an antiderivative of e to the u. So this is going to be pi over negative 4. That guy's still up front. Now the antiderivative of e to the u is, well, e to the u. Right? Because e to the u is its own derivative. So what would you differentiate to get e to the u? Well, e to the u. And e to the u is now evaluated between 0 and negative 4 natural log of 2. Okay, so this will be negative pi over 4. Okay, and then this right here is going to be the following. It's going to be e to the negative 4 natural log of 2 minus e to the 0. All right, because I'm going to plug these guys in. So this is going to be negative pi over 4 times e to the negative 4 natural log of 2 minus 1, like that. Now this right here can be separated. We've got e to the negative 4 times e, whoops, excuse me. We have e to the negative 4 raised to the natural log of 2, or we could rewrite it as e to the natural log of 2 raised to the negative 4. Well, this guy right here is pretty slick to work with. Okay, so e to the natural log of 2 is just equal to 2. So this guy right here is just 2 raised to the negative 4, which is 1 over 2 to the 4th, or 1 over, let's see here, I think 16. So this is just 1/16. So this would be negative pi over 4 times 1/16 minus 1. Okay, so let's just finish this guy out. We're almost done. So 1/16 minus 16/16 is negative 15/16. Okay, so it's going to be positive, and so that'll be 15 pi over 64, it looks like. Now there's another way of doing this, so I'm going to go ahead and show you. If you don't like this whole changing the bounds and stuff, you don't have to do it that way. Okay, so when we get to, okay, so let's go from right here. Okay, this guy. So what we can do with that guy is we can say, well, I'm just going to rewrite it down here so it's a little bit neater. So this is the way that I usually do it. Okay, what I do is I always say, okay, let's let u still be equal to negative 4x. Again, that still implies that du is equal to negative 4 dx, which implies that du over negative 4 is equal to dx. So what I'm going to do is I'm going to replace it in here, but I'm going to leave my bounds the same. And so this just kind of gets you past having to change your bounds. And so this would be e to the u, and then du over negative 4. So again, we're going to pull the negative 4 out. Everything is roughly the same. That's eu du like that. And so this will be pi over negative 4. And now, let's pull this out. This is going to be, again, this is e to the u. Now, it would be e to the u evaluated between the bounds, but I'm going to replace u now. So instead, I'm going to go back to say, okay, well, what was u? Well, u was negative 4x. And now we don't have to change the bounds. So just a quick recap. What I'm doing here is I'm saying I'm going to do the whole thing, except once I get to my evaluation using the fundamental theorem of calculus, Once I get to that evaluation, I'm going to take this guy right here, which was u, and instead of changing the bounds, I'm just going to replace it back with what u was. Now watch, it'll give you the same value. So this will be negative pi over 4, and this will be e to the negative 4 times the natural log of 2 minus e, like this. So this will be e to the negative 4 natural log of 2 minus e to the 0, which is 1. And if you notice, this guy is exactly like that guy. Okay, so that's how we go ahead and solve a problem like that.